Okay, look at this question now. The question says a balloon which always remains spherical on inflation is being inflated by pumping in 900 cubic centimeter of gas per second. Find the rate at which the radius of the balloon increases when the radius is 15 centimeter. So this balloon is spherical always. It always remains as spherical as you inflate it. So basically you are talking about a sphere. This is being inflated by pumping in 900 cubic centimeter of gas. So every second you pump in 900 cubic centimeter of gas. So that is the rate at which the volume is increasing. So we say dV by dt is equal to 900 centimeter cubed. And your question is to find the rate at which the radius of the balloon increases. So I want the rate of change of radius with respect to time. So dr by dt is equal to question mark. So what should I do now? Establish a relationship between V and R. And the relation is V is equal to 4 by 3 pi r cubed. So I have a relation between V and R. So I can differentiate this with respect to t. Differentiating with respect to t, derivative of V with respect to t will be dV by dt. So I have dV by dt is equal to right hand side is this 4 by 3 pi is a coefficient which stays here, and r cubed derivative is 3r square into dr by dt because I am differentiating with respect to t. So derivative of r cubed is 3r square into dr by dt. Here dV by dt is known to me, so I'm going to put that value in. dV by dt is 900, here 3 and 3 cancels, so 4 pi r square dr by dt. So I solve for dr by dt, so dr by dt is 4 pi r square goes to the other side and divides 900, so 900 by 4 pi r square. And in the question they say the radius is 15 centimeter, so I use that value now. So this is actually 900 by 4 is 225 by pi r square. So 4 cancels with 900, 225, and I put the value of r in. When r is 15, 225 divided by pi into 15 square. 15 square is another 225, so it gives me 1 by pi centimeter per second. So that's the rate at which the radius is increasing. We look at another question now. It says a water tank is in the shape of an inverted cone. So that's what I have drawn here, an inverted cone. So that's a water tank. So what they are saying is it has a semi-vertical angle of tan inverse of 0.5. So what I did is, when I draw the altitude, the height of the cone, I get the semi-vertical angle here. This semi-vertical angle, I named it as theta. So what they are saying is that this theta is tan inverse of 0.5. Theta is tan inverse of 0.5. So I said theta is equal to the semi-vertical angle, which is tan inverse of 0.5. That's an equivalent relation. I shift this tan inverse to the left side. If I shift tan inverse to the left side, it will become tan theta is equal to 0.5. So I write tan theta is equal to 0.5. That is a relation which I know. Now what they are saying is that you are pumping in water. So water is being poured into this at the rate of, it says 5 cubic meter per hour. 5 cubic meter. Water is being poured into this at the rate of 5 cubic meter per hour. So water forms a water cone inside like this. So it's a variable cone. Every minute its volume increases at the rate of 5 meter cubed per hour. So its radius changes, its height changes. So r and h are variables. So what I am trying to do is, your question says find the rate at which the level of water is increasing. So what you need to find is dH by dt. What is the rate at which this height is increasing? And the first thing is what I notice is that this tan theta is equal to 0.5. I can make use of that relation. What is tan theta in this diagram? Tan theta is opposite side by the adjacent side. So opposite to theta is r, adjacent to theta is h. So tan theta is actually opposite side by adjacent side. R by h is equal to 1 by 2. I leave it as equation number 1. And then it says dV by dt is 5 meter cube per hour. You are pouring in water at the rate of 5 meter cubed per hour. What are we looking for? dH by dt is equal to question mark. So now I need to establish a relationship between V and H, because dV by dt is given to you. You are pouring in water at the rate of 5 meter cube per hour, so volume changes at that rate. And they want us to find out the height at which the water level is increasing, that is dH by dt is question mark. So make a relation between V and H. We know that V is equal to 1 by 3 pi r square h. That's where we notice something. I wanted a relation connecting V and H. But what is this pi r doing here? R is also a variable. I don't want this r here. That's when it strikes you, okay, we have this equation here. R by h is equal to 1 by 2. So can't I solve for r from here by cross multiplying h? So if I do that, I get r is equal to h by 2. So I can take this value of r, which is h by 2, and plug it in here. In place of r, I take this value h by 2 and sub it in here. So my v is going to be 1 by 3 pi, which stays there. In place of r, I put h by 2 the whole square into h. If I simplify, this is h square into h is going to be h cubed. And this is 2 square, which is 4. 4 into this 3 is going to be 12. So what do I get? 1 by 3 pi into h cubed by 4, which is pi by 12 h cubed. 3 fours are 12. Pi by 12 h cubed. So that's my v, and now I differentiate with respect to t. When I differentiate, derivative of v is dv by dt. Pi by 12 stays there. H cubed derivative is 3h squared into dH by dt. And I know the value of dV by dt, which is 5. I'm going to sub it in here and then solve for dH by dt. So I have the value of dV by dt substituted here. Now cross multiply, rearrange for dH by dt. So 4 goes to the other side, makes it 20. Pi h square from top will come down, meter per hour. Now the h value is given to you as 4. Plug it in into this 20 by pi h square. So 20 by pi into 4 square. 1, 4 and 20 will cancel. 4 goes in 25 times and the denominator is 4 pi meter per